In this video, I'll be going over some of the knowledge and technical information regarding waterjet cutting, specifically for the PROTOMAX built by OMAX. Here's the shareable link to this presentation if you'd like to access that. This link should be up and working. If not, sorry. How it works. Waterjet cutting works off of erosion. Pressurized water is directed into a fine stream that accelerates garnet into and sequentially through the material you're trying to cut. Water and garnet is pumped through a 30,000.03 mixing tube, also known as a nozzle, at 30,000 psi, pounds per square inch, with a 5 horsepower electric pump. Pumps on larger water jets are more probably in the 20 to 30 horsepower range. The PROTOMAX is limited in horsepower size for its pump, which influences its maximum cutting capacity. The garnet is a fine abrasive sand that does the cutting, not the water. The water is specifically just a way to get the garnet through the material, kind of acts as a vehicle. You can see here that the abrasive is added to this water jet stream, and then it comes out as a water and abrasive mixture at 30,000 psi because it's being forced through a very small orifice. A water jet can cut a variety of materials, basically all materials. Some glasses cannot be cut because they'll shatter, and sometimes pre-drilling is required for cutting out a part and not relying on the water jet to actually do the piercing. So the pre-drill is done with a drill bit. Sometimes those drills are actually attached to the head of the water jet gantry. Water jets primarily work great on all metals, all composites, and plastics, woods, basically anything that won't actually get damaged by water. Cutting a phone book might not result in the best results because the paper is going to get damaged by the water from the water jet. Why water jet cutting? Obviously, you can use a water jet to cut flat parts. Maybe those flat parts are a finished product. Maybe they just need to be slightly deburred or polished. Maybe they get bent or welded into an assembly. Water jets can cut composite materials, so they're very popular in aerospace applications. And water jets can also be used for stock prep for secondary processes like machining. Water jets also have the ability to cut with either a fourth or fifth axis, meaning the material either rotates on a fourth axis like you're cutting out a shape on a pipe or tube, or the head of the water jet can swivel as seen here, and you can cut out some complicated shapes with the fifth axis. Here we kind of have a 2D flat part, kind of looks like some type of engine flange thing. Here's some relatively thick parts. Some water jets can cut up in excess or up to 6 to 8 inches of material. Once again, that's dependent on the horsepower of the pump, and also run times can be rather significant or long with the thicker material. Here we have two examples of water jet cutting the rough geometric shape of the part that is then put inside a CNC mill or lathe possibly to create the part to finished size. This is a lot more faster because most of the material is already removed with the water jet, and it's less time spent in the machine where the material is removed with an end mill. Some water jets have dual heads where you can cut out two parts at the same time. Typically the same parts, is just running a double quantity setup. Benefits of the PROTOMAX. This can also be applied to water jets in general. There's no heat affected zone, so that means there's no warping or change to the material. Operations like plasma cutting involve heat, and that can cause the material to warp and also impacts the edge of that material where the cut is. Same thing would be applied to laser cutting. Some knife makers prefer to have their knife blanks water jet cut because there's no heat affected zone. Water jets have a high level of accuracy. That accuracy is ultimately dependent on the material thickness and the quality and the machine's capabilities, but definitely a lot better than doing stuff by hand. There's a high level of repeatability, getting consistent results. There's less cleanup on the part, especially when compared to a plasma cutter. The backside of the material is relatively clean. There might be a very, very small burr, but it's nothing like the cleanup that is required on a plasma cut part. And like I've said before, cuts a variety of different materials, not just metal like what a plasma cutter can only cut. There are some downsides to a water jet cutting. Specifically in the PROTOMAX, you can only cut in a 12-inch or 1-foot cutting area, as seen right here. So you are limited by the part size that can be cut. It is a relatively slow operation when cutting thick materials. Other applications like using a bandsaw might be faster if you need to cut rectangular shapes, but for intricate patterns or geometric shapes, it's still probably going to be the fastest bet, but you do need to factor in the runtime of the machine. That runtime also dictates the high operating cost, where the consumable garnet is used up during the cutting process, so you need to be aware of the costs of running a water jet. Other information. For us, cut paths are programmed in Autodesk Fusion 360. Basically, you can create your model in a variety of CAD programs, whether that's Fusion, Rhino, Inventor, SolidWorks. That file is then programmed. We program that file in Fusion, then Fusion makes the G-code via a post-processor, and then there's a software program called Make that actually runs the G-code off the flash drive and controls the machine. Fixturing. The material holding system fixture secures materials while machining a part. Fixturing prevents the material from moving, vibrating, floating, tipping, or falling into the tank, all of which I have personally experienced. The abrasive jet stream is very powerful. The force exerted from the abrasive jet water stream into the tank can move or float the material during the cutting process. If the material moves during machining, the part will not be precise and may be ruined. There's quite a bit of upward flow of water coming from the bottom of the tank up after it bounces around in there. That could definitely move your part. Also, sometimes your nozzle can collide with scrap pieces or offcuts or little tiny sections that float up. That can sometimes be moved if your material is not clamped down. Sometimes these clamps, as illustrated right here, little spring tension clamps, aren't going to completely hold it permanently in place, but they definitely hold the part or stock in place during the cutting operation. On larger water jets, sometimes you see large plates, big chunks of metal that are used to weight it down, or some type of mechanical clamp. And if the material is big enough, I imagine the weight of itself could be good, but for the most part you do need some type of fixturing. The XYZ, the cutting stages of the water jet, the PROTOMAX specifically, provides a 12-inch by 12-inch cutting envelope. The Z-axis allows manual up and down movements for cutting materials up to 1 inch thick. You can see the Z-axis right here, and then we have our Y and X moving left to right. This would be considered the front of the machine, the back of the machine, the left and the right. When looking down on the table, the X-axis runs left to right, the Y-axis runs front to back. The Z allows for vertical movement of the cutting head. This is done manually by loosening this knob and pulling this assembly up. When the PROTOMAX is homed, the nozzle is moved to the position X0, Y0 coordinate at the lower left of the cutting envelope. Basically, if you're over here and you need to home it, it's going to slowly go to one side, and then the PROTOMAX computer knows where the actual machine is or the location of the cutting head, and that is important. This is basically a 2-axis machine. The Z distance or coordinate location of that doesn't change. It's set at a fixed height, and it only moves in X and Y. The cutting stage has a removable slat bed assembly to support cutting materials. The slat bed assembly is removed to access the cutting tank for cleaning and maintenance. The tank does catch all the garnet and scrap parts and parts you accidentally drop down in there, so they do need to be cleaned out every now and then and removed. The slat bed assembly is secured to the cutting stage frame and provides support for the part being machined. So these cutting slats right here that run front to back get worn out. They get cut into. They're not going to get cut all the way through in one cut, but they do get worn out, and typically through scheduled maintenance or routine maintenance, whenever we need to do it, we will rotate or flip and then ultimately replace the cutting slats. Larger water jets are going to have much bigger cutting slats, and they might be changed more often depending on the amount of cutting. If the cutting slats are not supporting the material, there's going to be some bowing, and that will ultimately possibly result in nothing good. The power switch is located on the right side of the machine. It's kind of a big yellow knob that you turn it to turn it off and on. Basically, the best way to know that the PROTOMAX is on is whether the LED work light inside of the machine is on. That illuminates the cutting stage. The garnet delivery system consists of a high pressure nozzle, which is kind of in here, a garnet abrasive feed system, which is the hopper, that's where the garnet is stored, and then in a feed tube where the garnet's going to flow or actually get sucked through here, up in here, down here, and around here, and then it's plugged into this area of the kind of nozzle area, and that's where it mixes in the mixing tube with the high pressure water. The garnet abrasive hopper lid keeps the garnet abrasive from being contaminated with debris or getting wet. We got our lid right here. There's a screen right here that helps prevent small pieces of debris when filling the hopper that may clog the feed tube or the nozzle. Definitely a clogged nozzle is not good. Sometimes they can be unclogged, sometimes they cannot, and they're expensive. Not all of the garnet particles are completely crushed to specification. Occasionally you'll find like a little pebble-sized piece, or maybe a piece of FOD from something else that shouldn't be there, and we need to make sure we always pour our garnet through the screen. When machining a part, the garnet abrasive flows from the hopper to the abrasive water jet nozzle through the feed tube. That feed tube's kind of plugged in here, so the garnet's up in here, and this is where there's a hole on this backside, and the feed tube goes in here, and basically some like scientific suction is made that sucks the garnet at a constant rate from the hopper and out the nozzle. You can see the garnet kind of funneling down, emptying in the hopper. If you don't see the garnet moving, getting lower, there's a clog and it needs to be fixed. The garnet abrasive material in the hopper must be kept clean and dry. If moisture enters the hopper, the garnet abrasive material will clump and clog the feed tube, which will require cleaning, and that takes approximately 10 to 15 minutes. What else? Sometimes the garnet kind of builds up along the side and it's getting sucked in the middle, so it might look like there's still garnet in the hopper, but it's actually empty in the middle where it actually gets sucked. So I like to keep this kind of half full, never really fill all the way to the top, because sometimes when you have a nozzle clog you have to drain it and empty the garnet out, and that's just a way to make sure you don't contaminate that much garnet, because if the nozzle gets clogged, the water is going to kind of backflow through the feed tube and start squirting out the side. It does squirt out this side right here, but we just want to make sure we keep all our garnet dry. The Z standoff is the distance from the nozzle to the material. So material, nozzle, nozzle, material. This distance or gap. It's set at the highest point on the material. Your material should be relatively flat, but if there's a little bit of a bow in it because of clamping forces or thin material, you want to make sure that you set it off of the highest section or spot on that material. This Standoff is a shim ranging from 60 thousandths, 0.06 to 0.08, and we actually have a 0.075. We have a couple different shims. Not exactly sure what the best one is. The PROTOMAX originally came with a 0.060. Now we're running a 0.075 shim that sets the perfect distance from the nozzle to the material. You set this manually by loosening this clamp or knob. That's going to relieve the clamping pressure on this bracket, and then you can lift or lower this manually by hand. It's best to kind of keep your hand on it gently so it doesn't slam down into the material or one of the deck slats, and that will hopefully prevent any damage to the nozzle. The water level in the PROTOMAX. It's best to cut parts underwater when possible, so your part is actually submerged underwater. This will lower the noise of the water jet and also reduce the mist and splash created by the water and abrasive, ultimately keeping the machine cleaner. Cutting underwater also helps the garnet bins collect cutting debris instead of allowing the debris to settle in the tank. So on the left side and right side, you can kind of see it right here. There's this catch tank on the left and the right that will catch some of the garnet and debris right there, and that's a lot easier to clean. Typically we want to have about 1/4 inch of water above the material. That will work best. To set the water level, we have an auxiliary hose plumbed into the PROTOMAX, and you just turn that on, and that allows the water level to raise. The level is lowered or raised by the height of this snorkel over here. It's kind of like it basically looks like a snorkel with a little screen on it. It's flexible. You kind of bend it down, it'll lower the water level because that's where the water is going to drain into our water recovery system, aka the filter bag. To raise the water level, you need to make sure that the snorkel is up high, and then you turn the water on. If you leave the water on, it will not overflow because this snorkel height is set, and there's also like a backup snorkel in the back to prevent water from completely overflowing from the edge of the PROTOMAX. Tabs. This is something you'll learn about when you're programming your part for the Waterjet. Tabs keep the part attached to the stock so they don't fall into the tank. Example here, some of these parts are pretty small and they might tilt up and fall and drop down into the tank, and it's not a fun process to kind of go elbow deep in the garnet abrasive water and retrieve your part. So adding a tab keeps it intact with the stock. Tabs can be broken by bending or cutting with a tool. Typically you can just snap them off with your fingers. Sometimes you will require a cutting tool like pliers or a small saw. Usually one tab gets the job done, but should be placed where it's easy to break. So this tab right here, it's nice and sturdy. This section is going to break right here. If we added the tab right here, it might snap off a little bit, but it also might bend this prong section. It's also important to put a tab in a spot where you can actually deburr it, because there's going to be a little piece of material left on because it's going to break right about here. You need to be able to sand or grind that down. 0.06 is a good small tab for the PROTOMAX. That setting is programmed in Fusion 360. Basically, any thinner, you're going to get smaller than the diameter of the nozzle, which is the kerf, and therefore your tab's just going to basically not melt apart, but be cut away and not even be there. If you go too wide, like 0.1, 0.125, that's a pretty thick tab, or too wide of a tab, and you're going to have a difficult and regrettable time trying to break that off. So that's that for tabs. Stock offsets in the work coordinate system. This is pretty important for not making mistakes. The standard stock side offset is about 40 thousandths, 0.04, a little thicker than the nozzle or kerf width. This is the extra material around your part or tool path as seen right here. So this is our stock size, and we add a little bit extra from the overall size of our part. There's no top offset because the Z thickness is the same as our material, which is the same as our part. The work coordinate system, the WCS. There's a standard work coordinate system that pretty much we'll use all the time whenever possible, but it can be changed if necessary. That work coordinate system is basically the XYZ home location of your part, not the home location of the machine, but the home origin of your part, also known as G54. This is where all measurements are going to be taken from and referenced. So we like putting this in the bottom left top corner right here, so it's repeatable. If everybody has the same work coordinate system, there's a less chance of scrapping parts. If you have the wrong work coordinate system, most likely you're going to be cutting outside of your stock area where you want, and maybe you only cut half of your part. Cut quality or edge quality. How accurate your part is or how long it takes to cut is influenced by the cut or edge quality. The higher the cut or edge quality, the better or more accurate your part will be. A higher quality results in longer run/cycle times and more garnet is used. In Fusion 360, cut quality is set on low, medium, or high. Auto is also an option. Low works totally fine for most applications. You can specifically program certain features of your part to have a higher quality. Maybe you have a certain geometric shape or a bolt hole pattern that needs to match up with another part for an assembly. That can be cut at a higher quality. The OMAX and Telemax software assigns cut quality, it's called edge quality, where it's Q1 through 5, and you can see those cut qualities right here. So quality 1, pretty rough, quality 2, 3, 4, and 5. This mainly influences the speed at which it's cutting. So a lower quality will cut faster, high quality cuts slower, making sure it's getting a nice finish. As the water jet is actually cutting out the part, that kerf or the beam or stream of high pressure water and garnet's actually flexing and bending because the machine is moving and that water is kind of still coming down straight, but it flexes a little bit, and you can see that here. The faster the machine goes, the more there's going to be that flexing or flexing, we'll just call it that. Deflection, that's a good word right there. Okay. Next question, part statistics. When you plug your flash drive into the laptop and open up the Make program, you open up your file, you'll be able to look at some of the statistics on your part. Basically, you verify your material, your thickness, whether it's rotated, and it mainly gives you an estimated time for your path, so less than 2 minutes for this part. Don't recall what part this was. And it also gives you an estimate on how much garnet you need. Those two things are really important because time plus garnet equals money. It shows the number of pierces. That can also factor in with how long it takes to run a part because some materials take longer to pierce, especially with thickness, and it gives you a total tool path length. So take a look at the part statistics. Look at the estimated cycle time for math. This is a type, I don't even know what I mean by this. I don't know. But basically, if you see well, you kind of do the math on it where if you have a cycle time that's 20 minutes and it's a small part, there's probably something that's wrong. But if it's 20 minutes and it's a large part on thick material with a lot of detail, then most likely it is correct. Here's a bag of garnet, 55 pound bag. We get this in the 1 ton bag. Path setup. When you're opening your file, you need to select what material you're cutting. It has a pre-programmed machinability number. This influences how fast the water jet moves and how long it spends piercing. You tell it how thick it is because that also influences how fast it cuts and how long it spends piercing. There's an option to adjust the tool offset, which is basically the width of the kerf, which is the thickness of the cut if needed. So let's say your part's a little bit big, you would actually make this number a little bit smaller, and that will compensate and offset for that distance or difference. You can rotate your part directly in this section. A lot faster to rotate it here than going back into Fusion and re-rotating it and programming it and post-processing. You can also scale your part right here to make it bigger or smaller based off of a percentage. So 1 is 100%, 0.5 would be making your part half as small, and 2 would be doubling the size. And that's going to double the size of everything. So if you're making your part small, your tabs are going to get smaller most likely, and are not even going to be there. If you make your part bigger, your tabs are also going to get bigger, and those might be a little hard to break off. Basically, the workflow for modeling and programming in Fusion 360 for the Waterjet: draw your part. That part can also be drawn in another program like Rhino, export it as a DXF, extrude it to make it a 3D solid. It's not really necessary, but it's a nice little feature to do. You're going to switch to the manufacturing workspace in Fusion, create a setup, add the stock side offset, click on the work location, the location of the WCS, which is the top bottom left corner. Create a cutting operation, select the tool, edit that tool to the right diameter of the kerf, select your quality that you're going to use, and select your geometry. Add tabs, change the lead-ins and lead-outs. I'd recommend going back to this slide when you are in the process of programming your part. Pick entry positions if necessary, so you can have it start at certain locations on your part. You can run a simulation to make sure everything gets cut. And then finally, basically post-process onto a flash drive that makes the G-code, and that is opened up in the make software that actually controls the machine and makes the part. The make software makes the part. Common mistakes: running out of garnet. The nozzle is still moving, but it isn't cutting all the way through. It tends to spray more and isn't as loud. So if you run out of garnet, you should stop your part. You need to add more garnet and then recover, or basically start over, because no garnet equals no cutting. Keep an eye on your machine. It will still look like it's possibly cutting to the untrained amateur eye, but it's spraying more because all that water is not going through the material into the bottom of the tank. It's splashing up to the top. And the garnet flowing through the machine actually makes it louder, so no garnet equals a little bit quieter machine. If you don't see the garnet being sucked through the hopper, that's an indicator that the garnet is either out or there's a clog. Sometimes the hose can clog, not the nozzle, but the hose, the feeder tube. Another common mistake is a clogged nozzle caused by debris, wet garnet, or the material touching the nozzle. The machine goes very quiet and the water is squirting out the abrasive feeder tube by the hopper. Stop the machine immediately when the nozzle is clogged. So sometimes it can be out of garnet and it's not that easy to tell. But when it's clogged, it's really easy to tell because the water is not shooting out of the nozzle at thousands of psi. It's kind of squirting out the side, and it sounds different, very different. Stop the machine immediately when the nozzle is clogged, and that just involves lifting the lid. That's the fastest way to stop the machine. And you'll have to perform a nozzle recovery, and I'll have a separate video for that, and that takes quite a bit of time to do. Hopefully you can recover the nozzle. Cutting out your part off or outside the stock, that's definitely not good. That results in having a part that's too big for your sheet metal or the incorrect location of your work coordinate system. Running a dry run usually prevents this. A dry run is where the nozzle kind of jogs around the part but is not cutting, hence the name dry run. Excessive cycle time, runtime due to incorrect material type, thickness, and cut quality. So if you select the wrong material, maybe it's going to cut all the way through, but it's going to be cutting all the way and it's going to be very slow. So example, you're cutting plastic but you leave it on a metal setting, that's going to be a lot slower. If your thickness is incorrect, if you are cutting 0.1 and you leave it on 0.2, you're just going extra slow. And that same thing applies with cut quality. If you leave your cut quality on high, that's going to increase the runtime. Parts not cut all the way through, basically if you select the wrong material or thickness, or you run out of garnet. Those are the 2-3 things that will prevent a part from being cut all the way through. Clogged nozzle is a whole nother thing that obviously won't cause the part to be cut all the way through, but that's something a little different, and it's more of like a crash. Don't use the washdown hose or extra hose when it's cutting. So basically you do not want to take away water pressure that's being supplied to the machine while it's cutting. A lack of water pressure results in a lack of cutting and will air out the machine, sometimes clogging the nozzle. Not setting the Z standoff, that thickness or distance from the nozzle to the material needs to be set at a specified thickness based off of the standoff shim. Be aware of the dead zone outside the cutting window. So possibly hard to explain, but basically the cutting table or area is 12 by 12, but there's this area around it because you might want to put in a part that's like 13 by 13. So you can physically still put a larger part in the table, but it might not be able to cut all the way. So you kind of need to know where that 12-inch window is that you can cut. Not clamping down your material will result in your part shifting and ultimately most likely scrapping a part. Not putting tabs will result in your small pieces dropping down into the tank, or medium-sized pieces kind of tilting up, getting caught, getting recut accidentally, or tilting up and causing a collision with the nozzle, which typically will move the material. Not watching the filter bags, so we have a filter on the side that filters out the old garnet water, so that sometimes gets a little full and we need to swap out the filter and it just overflows. So check that out, keep an eye on it, and do not leave the water jet unattended, because basically immediately when you walk away something bad might happen, like a crash or a nozzle getting clogged or running out of garnet. Keep an eye on it. You can listen to it a lot. You don't always have to be watching everything, but definitely don't leave it unattended. Best practices, these are things you need to do. Be aware of your cut quality. Higher cut quality takes longer, but it results in more accurate parts if that is necessary. Conduct a test cut in between the slats, not over the material, to verify garnet flow. It's basically you're turning on the water jet, it's flowing at 30,000 psi, but you're not actually moving or cutting anything. It's just kind of a test. Know your material thickness before you clamp your material onto the table. Try to use 2 to 3 clamps whenever possible to secure the material. Conduct a dry run to check for clamp collisions and make sure there's enough stock. I've had certain students cut all the way through the clamps because you can't really see it when it's submerged, but you should be able to catch that during a dry run. And make sure the Z is up a little bit so there's no collisions when performing that dry run. Always zero your nozzle location and return this location after a dry run. You have to go back to the path start. Otherwise, it will basically start cutting wherever the nozzle currently is. So you have to move it back to that original WCS location. Double check your material type and thickness. Keep the nozzle cup up when doing a dry run and down when cutting. That nozzle cup's that rubber orange yellow thing that helps prevent the splashing. Nest your parts together to reduce material waste. Keep everything nice and close together. Pause the machine when needed, so there's a pause button, or you can also lift the lid. It's not really an emergency stop, even though it does stop it in an emergency, and then there's a play button so you can resume where you left off. This is really important when you're removing those floating pieces that kind of get cut and then tilt up a little bit or start floating away, because those floating pieces could cause a collision. Don't drop stuff like clamps in the tank. If you do, retrieve them. Raise or lower the snorkel to change the water level. Like I've mentioned before, keep an eye on the filter bags and the water level inside the bags. Rinse the cutting bed inside the machine. Rinse the cutting bed and inside the machine when done. So basically on all the components inside, all that garnet adds up. We need to make sure you keep the water jet clean. Always add garnet through the metal mesh. There's a forward reverse path to pick up where you left off, so if you do have a mistake in a part, you might be able to finish it. Put your leftover stock away or in the appropriate scrap bin, so not leaving your stock material in the water jet. Only cut flat material whenever possible. Don't leave it unattended. Check the estimated runtime. It was kind of a verification step to make sure everything is correct. And there is a setup checklist, and main thing, make sure the water faucet is on before you're working with the water jet. And then you should also select the closest material in the library and the make software. Not all materials we have are currently in there, but there's ones that are pretty close. So as far as resources, here's the PROTOMAX website, the OMAX website. There's an online community for the PROTOMAX, and then a knowledge base, and then some of my YouTube videos. This is a little simple sample one. Notice the yellow cup is flipped up. This is for filming purposes only, so you can actually see what's going on. This is not a water jet, that's a magnetic brake. This is 80,000 thick aluminum. There's a thicker, almost 1/4-inch plate aluminum. Notice the cup is down now because it takes longer to pierce, and this is kind of a slower operation. You can see some of the garnet build up on the surface of the material. Sweet. Well, that's basically everything you need to know, and pretty much like 99% of everything I know about the water jet. Thank you, and once again, you should be able to look at this presentation on your own with the link at the beginning, and possibly linked in the description below. Thanks.